Hello everyone, welcome back to this series on solutions to previous year GATE chemical reaction engineering questions. In this part, that is part 3, we will be looking at questions from GATE 2023. So let's move on to the first question. CO and H2 participate in a catalytic reaction. The partial pressures of reacting species in the feed stream are PCO and PH2. While CO undergoes molecular adsorption, H2 adsorbs via dissociative adsorption as hydrogen atoms. The equilibrium constants are KCO and KH2 for the adsorption steps. The total molar concentration of active sites per unit mass of the catalyst is Ct. The adsorption steps are at equilibrium. And which one of the following expressions is correct pertaining to the ratio of concentration of catalyst sites occupied by CO to that of hydrogen atoms? So let's look at the solution to this question. So it is given that CO adsorbs molecularly. So hence we can depict this equilibrium reaction as CO plus star giving CO star. So here star represents the active site and CO star represents the molecularly adsorbed CO on that particular active site. The equilibrium constant for this reaction is Kc. Also, the hydrogen is known to adsorb dissociatively. So hence H2 will interact with two active sites of the catalyst, giving rise to 2H star, which is basically two hydrogen atoms adsorbed over two active sites of the catalyst. The equilibrium constant for this step is KH2. Now, according to the definition of equilibrium constant, we can write for KCO as CCO star divided by PCO into C star, which is basically concentration of the product divided by the product of the concentration of the active site and the partial pressure of CO. Similarly, we can write the equilibrium constant for hydrogen as CH star square divided by PH2 into C star square. So considering this as equations 1 and 2, we need to find the ratio of concentration of catalyst sites occupied by CO, which is basically CCO star, to that of hydrogen atoms, which is basically CH star. So we need to find the ratio CCO star by CH star. So from equations 1 and 2, we can write CCO star as KCO into PCO into C star divided by C star into root of KH2 into PH2. Further, we cancelling out C star, we get the ratio as KCO into PCO divided by root of KH2 into PH2. So hence option A is the right option for this question. So let's move on to the second question. The question says, fresh catalyst is loaded into a reactor before the start of a following catalytic reaction, A giving products. The catalyst gets deactivated over time. The instantaneous activity A of T at time T is defined as the ratio of rate of reaction RA prime to the rate of reaction with the fresh catalyst. So from the control experiments, an empirical relationship for RA prime as a function of T is given. We need to find the activity of the catalyst at T is equal to 10 hours. So let's look into the solution to this question. So we have been given an expression for instantaneous rate as minus 0.5 T plus 10. So we need to find the instantaneous activity, which is given by the ratio of rate at a particular time divided by ratio of rate when the fresh catalyst is loaded. So this is basically RA prime at some T divided by RA prime at T is equal to 0, because at T is equal to 0 is when the fresh catalyst is loaded to the reactor. So from the given instantaneous rate expression, substituting the values of T as 0 and 10, which is the required, which is where the activity of the catalyst is required. So we get activity as minus 0.5 times 10 plus 10 divided by minus 0.5 times 0 plus 10, which is basically 0.5. So hence the correct answer to this question is 0.5. So let's move on to the next question. A unimolecular irreversible liquid phase reaction A giving P was carried out in an ideal batch reactor at temperature at capital T. The rate of the reaction minus RA measured at different conversions XA is given in the table below. This reaction is also carried out in an ideal CSTR at the same temperature with feed concentration of 1 moles per meter cube at a steady state. So for a conversion of 0.8, the space time of the CSTR needs to be found. So let's look into the solution to this question. So for XA is equal to 0.8, we know that minus RA has 0.05 moles per meter cube second from the given data. And it is given that Ca0 is 1 kilomole per meter cube. So we know that space time for CSTR is given by this expression Ca0 XA divided by minus RA. On substituting the given values for Ca0, RA and XA, we get tau as 16 seconds. So hence the correct answer to this question is 16 seconds. So let's move on to the next question. An irreversible liquid phase second order reaction A giving B with rate constant K is equal to 0.2 liters per mole minute is carried out in an isothermal non-ideal reactor. The tracer experiments conducted resulted in the following residence time distribution. The areas of rectangles in the figure are equal. Pure A is fed to the reactor at concentration 1.5 moles per liter. The segregated model mimics the non-ideal nature of the reactor. Find the percentage conversion of A at the exit of the reactor. So let's move to the solution. We have been given the values of Ca0, K and order of the reaction and the residence time distribution. So in the question it says that the areas of rectangles 1, 2 and 3 are equal. Now if we observe the breadth of each of this rectangle, they are equal as well. They are equal to 5 units. So since area as well as the breadth of each rectangle is equal, we can say that the length of each rectangle will be equal as well. So the length of one such rectangle is denoted here as y. So hence we can say length of each rectangle will be equal to y. Now we know that the area under the residence time distribution curve is 1. So here this is basically the areas of rectangle 1, 2 and 3. The sum of areas of rectangles 1, 2 and 3 will be equal to 1. So hence A1 plus A2 plus A3 will be equal to 1. Since they are equal, we can write this as 3 times of area of a particular rectangle. So area of one rectangle is length into breadth, which is y into 5 units. So 3 into y into 5 is equal to 1. On solving, we get the length of one rectangle as 1 by 15 minute inverse. Now we know that for real reactors, Ca by Ca0 is given as integral 0 to infinity Ca by Ca0 of an element which is behaving like a batch fluid into E dt. So for a second order reaction, we can write Ca by Ca0 element as 1 by 1 plus K Ca0 into T. So on substituting the given values of Ca0 and K, we get Ca by Ca0 element as 1 by 1 plus 0.3 T. So now substituting this expression for Ca0 by Ca0 element in the expression for the real reactors, we get Ca by Ca0 as integral 0 to infinity E by 1 plus 0.3 T into dt. Now, if we observe the residence time distribution, the value of E is non-zero only between the interval t is equal to 5 to t is equal to 15. Hence, we will have to break this integral into the range of 5 to 15 minutes. However, in this range, the value of E varies between 5 to 10 and between 10 to 15. So between 5 to 10, E value is 2 times that of y, which is basically sum of the two lengths of the rectangles 1 and 2. So hence E will be 2y between 5 to 10. And between 10 to 15, the value of E will be equal to y. So hence we'll have to write this integral as 5 to 10 2y divided by 1 plus 0.3t dt plus 10 to 15 y divided by 1 plus 0.3t dt. So substituting the values of y and integrating this expression, we get Ca by 1.5, which is the given concentration of P at the inlet, is equal to 2 by 15 into 0.3 ln 1 plus 0.3 into 10 divided by 1 plus 0.3 into 5. So this is the simplified form of the first integral, plus 1 by 15 into 0.3 ln 1 plus 0.3 into 15 divided by 1 plus 0.3 into 10. So on simplification, we get Ca as 0.419 moles per liter. Now we can write Xa as 1 minus Ca by Ca naught, which is 0.419 divided by 1.5, which is equal to 0.7. So in terms of percentage, we can write the conversion of A at the exit of the reactor as 72%. So hence 72 is the right answer to this question. So with that, we come to the end of this part 3. So stay tuned for part 4, which will look at the chemical reaction engineering related questions from GATE 2022. So if you like this video, please share and subscribe to this channel. And we will see you in the next part. Thank you.